So this is the bowling ball lab, and today is the day you get to work on the bowling ball lab with your partners. I'm going to assign you the partners in a moment, and the bowling ball lab will commence. Tomorrow, we actually roll the bowling balls. You don't have that much time, so therefore, I'm going to give you a fair amount of help with this to get this bowling ball lab set up, but you have to get the final answer figured out, which comes down to this. At what angle should you roll these balls so that when you release them at the same time, that they will hit? All right, so here's some thoughts. First off, I drew this X and Y axis and said we're going to start here at 0, 0 with the ball rolling. So picture yourself right outside the door to the port, except if you turn to the left, right before you were going to go in, if you turn to the left, do you get, if you look out those doors, you'd see Pagel? All right, and right there, you just rolled this bowling ball on a nice straight line. Okay, and we have this ramp all set up to roll it right on the line, and it'll work pretty slick. You're going to have one person in your group doing the rolling, another person in your group also doing rolling, a third person helping with aligning the angle, and the last person is doing the countdown. And you're going to count down to like 3, 2, 1, and then release, and then everybody gets there. It's a lot easier to time if you have something like that, like somebody counting down. And then you go, and then both balls release, and then hopefully they hit. And if they hit, you get the points. And if they don't hit, you don't get the points. But you get 4 tries. So you can adjust. And it's not like, oh, it'll be easy because I get to adjust. You better be really close in the first place. Because if you have to adjust and they were way off, then, ooh, that's really hard to get it within 4 tries. So if you get your equations right, you'll be really close if the balls miss. And then you'll say, okay, I think we need to make the angle just a little bigger or just a little smaller. All right, so what angle am I talking about? This angle up here. Now, get prepared to think. I know, at this point in the year, you don't really want to think anymore. You just want to get this over with. But this is one of those days where you're going to have to dig deep on the problem-solving thing. So this bowling ball is rolling, and why is there a 0, 0 in its equation right there? That's where it starts. And then what is that? 1.75. That was an assumed what? It's not the direction. The direction is that it's only heading in the x direction, and it's not heading at 0. It's going nowhere in the y direction. So that's the direction part. So then it's not a direction, it's the magnitude. How can you measure magnitude of a bowling ball? Well, you could weigh it, but that'd be kind of dumb. What's this more about? Speed. All right, so the next part in class right now, we are going to figure out what that number is going to be, and I'm going to tell you it's not 1.75. In fact, you can't use 1.75 because I'm going to show you at the end some help on how you do this lab, assuming a 1.75, but it's not. I have some of the lab groups are going to use 2.0 for the speed on that ball, and I'm telling you it's not. And it's also not 1.75. I'm hoping that you'll find out in a moment. I'm going to do that rolling right now. For those that are watching along at home, you're not going to be able to see this part, but it will tell you when it's done how fast that bowling ball went. Okay, so we're going to be not using 1.75, and I want you to figure out that speed. I told you 1.75 is off a smidge. And we just tested it in class twice. And were you guys coming up with more than 1.75 as its speed or less? A little less? 1.71. Okay, I've heard a lot of people say 1.71. That's probably our best guess at the speed. Okay, so now, do you get you have an equation here that has a vector equation for the ball that's rolling this way? Now we need a vector equation for the ball that's going this way. And it involves the speed somehow. But it's not quite so straightforward because it's not going that speed, which is 1. We figured out it's 1 for this ball. This one's going 1 meter per second. This one's going 1.71 was our best estimate. It's not just going to throw that 1 into the equation like we could here, because why couldn't I just put a 1 here? Is it moving 1 meter per second in the y direction? No. Is it moving 1.6 or 1 meter in the x direction? No. You can't put it here either. So where do you put it? All right, this is the part where you've got a triangle, and I told you that this angle was the only thing you could set. Like, you'll have to figure out what that angle is. That's the only thing in this experiment you can control. You're going to release the balls at the same time, and you are going to get the angle right, and then they'll hit. It's the only thing you can control is theta. So at the end, you need a formula that has theta in it, and you're going to solve that. All right, so how do we get a theta into this equation? Don't I have most of this equation? Yes. And why are my lambdas the same? Think about it. Same amount of time. You're going to release them at the same time. Now, for the super advanced kids who get this on their first try, which some kids will, because they'll do their equations perfectly, they'll set it all up, they'll get a little bit lucky also, and it'll hit their first try. Then I'm going to encourage them to go off to the side while another group goes and try to do it with a 1 second delay. They'll have to rejigger their calculations and go, okay, ooh, I think I got it. My new angle is this. But don't worry about that unless it happens to you. If you hit on the first try, then cool, you should try a 1 second or a 2 second delay, which means the first ball gets rolling here, and then you wait like a second, and then you start the other ball. It's definitely harder, but just one little tweak in the equation. Okay, so what is the thing you don't know? These are the only things you don't know. I'm giving you these two numbers, 15.2 and 5 is where the ball is being released from. I got to tell you where that ball is going to start, and I'm telling you, it's at 15.2 meters over, like over this far, 15.2 meters, and then up 5 meters this way. I'll pause my video for a second. All right, so this is its starting spot, and you need these two things. And you need an angle. How in the world are you going to get something to put here and here that involves this angle and involves that it's going in the negative x direction? It's also going, by the way, in this direction, but I'm just trying to keep your life simple. I'm giving you one thing on the triangle, and somehow you have to factor in its speed, too. I must go somewhere. All right. I am going to pause for a minute while I let the groups work on this. Your goal is to try to figure out how to get two equations to hit each other. They got to collide, okay? And so two pieces, they have to collide, which is a problem like this. Remember these where you'd set up the little equations for it? I've done all the pre-work on this one. I've even written the two equations just to save you time. If you and your group cannot solve this and tell whether these collide, then you have no hope of doing the lab one, because this is the easy kind. But I'm trying to remind you how these work, because if you can't get two vectors to collide doing this, you definitely won't get two vectors to collide in the lab. So the first thing I want you and your partners to do is take this, which is all pre-set up. It's got two vector equations, and they're all already, equations are written, and see if you guys can agree on, do they collide, and if so, where? But our lab's a little different because we're going to make sure that they collide, and we won't know where. No group comes in knowing exactly where they're going to collide, but they come in knowing what angle they should use. Actually, that would be interesting if any group would figure that out, where they should be able to, in theory, if you know what the angle is, I think you should be able to figure out where they're going to collide, and you just make sure that your angle ramps are going to meet at that spot. That's an interesting thought. Never even seen any group do that. But back to you and your group figures out this solution first. Now pause for a second. One more thing to clarify. I did tell the kids they do intersect. You have to figure out where. But do they collide? I'm leaving that up for debate. Do they? I know they will go through the same spot, but will they be there at the same time? Okay, so the kids solved this by setting this equal to this, and use a different color here. This equal to this, and then doing some substitution, and they came up with two things. Lambda equaled one thing, and t equaled something else. What was lambda and t? 1/2, and t was? All right, you are correct. That means that if they cross paths, which these do, they're doing it at different times, which means that they did not collide. All right. On your case, do you get that you want them to collide? And so you have set their variables to be equal to each other. So that'll make sure that they will happen at the same time. All right, how about this? What is that place? Well, what do I do with the lambda to figure out that place? Plug it back in the equation. I put a 1/2 right here. And where will you be? At time 1/2, you will be at 1, 1. Whereas when you put in t equals 0 right here, that just cancels this part, and you're at 1, 1. So either way, the intersection spot is 1, 1. Now, how is the problem that we have different? Well, we aren't going to know an angle. We're going to have this weird thing. Well, you know some stuff. Has anybody figured out yet where the 1 would go? All right, in this triangle right here, that's the direction the ball is rolling. We don't know exactly what the angle is. We know it's going to be kind of in that direction. Do you agree that has some negative x component? Why negative x? Because it's rolling the opposite way as this one was when it was positive x. Okay, so there's some negative component to that distance. And this is theta. We don't know that. All right, I'm going to pause for a minute while you guys try to figure out what 1 means in this. 1 is the speed of it. You should be able to figure this out. I'm going to pause when you get that far. All right, just a little help down this road. What's the speed the same as? Magnitude. It's just a magnitude has units. I'll say, so what do we want the speed of? That blue side over here. We want the speed of this. Well, we already know the speed of it. It's 1, so therefore this is 1. Raise your hand if you had already come to that conclusion. That's smart. Good. Now, if that side, that's almost everybody. Good work. If that side's 1 and this side is negative x, or it's just a distance, we could call it plain x, it'd be okay, but that x would come out negative, then what's that angle? All right. To do this, I'm going to just remind you for a moment. Just a more simple question. I know I'm changing it. I'm changing it on purpose. This is different now. What if this was 5 and this was x? Could you tell me what theta is? No, you couldn't. But you could set up an equation for it, couldn't you? Would you use sine, cosine, or tangent? So would you be able to say the sine of theta was equal to 5 over x? Would you be able to get x alone? Yeah, you could. And you could get that x distance figured out in terms of a theta. So in other words, all you'd need to know is one thing, and that's theta. All right, so it's kind of like that. When you go back to this, and you see you've got this side's x, and you got this side's 1, remember the whole goal. What should go in here? What should go in there? I think that's enough that some people should get it before you walk out of here. It has to do with sine, cosine of the theta. And I'm not saying you'll be done and know, oh, theta equals 12. That's what you do at home tonight. But you got to figure out what goes in the 2 red circles. What goes in here and what goes in here. I'm going to pause for a minute while you try to figure that out. Okay, I can tell a lot of people are trying, and I could tell some people actually have figured it out. And I wish I had more time for you to struggle with it, but there's more to this problem than just figuring this part out. So, normally, I'm going to give you some more time to work on this, but considering the lab is tomorrow, and you still need to know what that angle is, has somebody figured out what needs to go in here and there Your best guess. I don't expect anybody to be perfect yet. So what do you think should be in the x spot? X equals, well, can you tell me the equation that involved theta and x? Just tell me that so people will get where it came from. I think you're on the right track. Sine of theta equals x over 1. So now do you know what x equals? Well, it kind of does. So if this is negative x, then now I'm going to solve for x, and, well, isn't x over 1 just the same thing as x? So negative x is sine of theta, so x is negative sine of theta. And this is the x row, isn't it? The top one? Negative sine of theta. Nice work. But don't just assume that. Tell me what equation you could get for this other part. Cosine of theta would equal, wait a minute. Couldn't we just do a different, cosine is just, that's adjacent over hypotenuse, we had sine over hypotenuse. So what are you going to do for the second one? I mean, I know you're just kind of assuming this must, if this one's negative sine, this must be negative cosine of theta, but can you show me why? What do you think? This is heading down towards 0, but I don't understand how that means. What do you think it should be? Just y? Just say it's negative y? Okay. All right, so then tell me an equation involving y and theta. Negative y over 1. So then what's y equal to? That looks like a little proof. Good. I know you said cosine is negative y, but I had to have the whole equation to show people where it came from. And so they don't just hear, oh, so this was sine, so the other one had to be cosine. Well, why? So this equation right here, cosine of theta equaled negative y over 1. That was the key equation to solve to get to this. And yay, y is negative cosine theta. And that goes there. Now, do you have the two equations? This is a simple question. Do you have this equation written down yet? Do you have this equation written down yet? Down here, this guy. Then don't you have the two equations? Except remember me saying you may not use 1.75 for that. We figured it out in class to be 1.71, and that's more likely to be accurate. Besides, if anything, the speed is even slower than that. Why? Because of friction. You are correct, sir. We don't have anything in our equation that handles the fact that the ball's going to slowly slow down over time. So it may start at 2 meters per second, but do you get it's going to get slower and slower and slower? So if anything, it's off in the direction of both speeds are probably off a little bit because that's how fast they start out, but maybe they slow down. Yes? That is very interesting. I get what you're saying. You're saying that if this ball is ever going to hit, it's going to be coming this way, right? And the other ball is going to be coming this way. At this moment that they hit, you're saying that if this distance is 5, then its y will have to have traveled 5. That's a very interesting observation. All right, so I want you to now finish this lab, which means what? That means you need to take everything that we've talked about here, and you've got two equations. You're going to try to figure out how to set these two equations so that they're equal, and then you'll be able to figure out what theta has to be. Or maybe you can just use what she said a second ago. Maybe that would be enough. Maybe that's enough to figure out theta. All right. So you better come back to your group tomorrow with what you think the angle is and why. I solved it this way. And you're mainly graded this time on the work that you're doing tonight, right now. I basically worked you through slowly to these equations. You'll have these equations if you were just paying attention. But do you do anything tonight with them? That's the part that I can grade you on. Okay, so do work hard on this. If you can get it to collide tomorrow with the correct angle, then that's going to be automatic full credit for the lab. Not a 100%, but automatic full credit for the lab, okay? But then people that don't get them to collide, how do they get any points? That's the work you do tonight. If you can't get them to collide, at least you got to show me I tried really hard, and these are the equations that I tried to solve. So if they don't work, in my opinion, try them again on a blank sheet so that you can show me, look, I tried this way and it didn't work, and I tried that one and it didn't work. I did a lot of work. Give me some part credit. And I will, as long as you have work shown. Even if you can't get the balls to collide, I'll give you some credit. I just can't give you as much credit as the groups that get it. All right, so hopefully you're going to get more than one try. The dream, they both hit on the first try. That's actually very difficult in the real world because there's little tiny aberrations like, oh, the floor is not slightly unlevel, okay? Or the balls slowly slow down over time, and we haven't factored it in. The angle that you set, we're going to try to make it as accurate as we can, but you might be off a smidge. You think you're doing 39.6 degrees, but you're not. There's all kinds of ways to mess this up. That's why you get multiple tries to make them collide. All right. So tomorrow, come in with what you think theta is and the work shown behind it. And that's your only homework for tonight. And don't let your group down by going, oh, I don't know. Okay. That's all I have for you for today.